So as I was saying about haversine distance, so these are the curved distances forming a kind of right angle triangle from which we can find out the sine, cos, tan, as you can see. So these, we don't have to go much into the underlying mathematics, which has already been implemented in the Python libraries, but just for your information. So we need to install this haversine library by writing pip install haversine. Since we are writing this command not at the command line terminal, we need to append this exclamation mark indicating not or negation. So in this Jupyter notebook, which is not the command line terminal, so exclamation. Now import haversine as HS, like pandas as PD, and for all the positions, that means how many ever longitudes are there or how many ever latitudes are there. You can take pickup longitude or pickup latitude or drop off latitude, longitude, anything, because their lengths are same. If you have a starting point, definitely you have an ending point in the data set because you have removed null values and all that. So for pickup longitude, for a particular index, say 0. So in the pickup longitude, you have so many values. Is that index 0, at index 1, at index 2, at index 3. So at the 0th location, whatever is the longitude, then whatever is the latitude, whatever is the drop off longitude and drop off latitude that you're taking over here. And then location 1 will be what? A location is always a combination of latitude and longitude. So the pickup longitude is this one, and pickup latitude is this one. Similarly, drop off longitude, drop off latitude. Location is a combination or pair of latitude, longitude. And then you pass both these locations as parameters to this haversine function. And whatever value you get will be the distance between these two locations. And then we are creating a distance column also. So for each of the positions, that means each of the values in the latitude and longitude column, for each of these particular start points and end points, we'll take their position, find out the distance between the start and the stop. And whatever the distance is, we are appending it into a list. And this list, we are writing it as a column in our data frame. Okay, just go through the code, you'll understand. And now we have added the column of travel distance by using the haversine formula calculation. Now, in Uber, the drives are always greater than equal to 1, their drive distance. And the distance of drive should be less than equal to 130 kilometers. This is a condition of Uber. Or maybe this condition is as per this data set that we need to imply. So only if the distance, suppose distance is negative, or distance is maybe 0, or if distance is some 1000 kilometer or something, such distances we need to ignore. So we'll create the data frame wherein the distance is greater than equal to 1 and it is less than equal to 130. Remaining observations, that means after removing the invalid distances, the remaining observations are these many. So if you compare the dimensions of the previous one and this one, you'll get a change. So now, if you want to create a Boolean matrix, whatever data frame you have, call the isNull function. So if the value is present, then it will denote it as false. If the value is absent, it will denote it as true. Right? We have already seen this. Now we need to plot a heat map. As we know, heat map is nothing but the correlation it indicates. So if it is indicating the correlation, whatever rows we have over here, you can map it like these are the columns. Suppose the column names are A, B, C, D. Here also we'll write it. And A is how much correlated with A will come over here. Suppose D is how much related to C, it will come over here. C is how much correlated with D, it will come over here. So each value is how much correlated with each other, that we'll get to see. And remember that since A with A, it is the same column, B with B, same column, C with C, D with D, same column. So along the diagonal, we'll have perfect correlation. That means if one value is increasing, the other value also increases. This is positive correlation. Perfectly, it will be at the diagonal. We have seen what is correlation, right? Now, if we want to perform correlation, whatever data frame is there, .corr, we need to call. This particular function, when called on the data frame, will create a correlation kind of structure in which we have the columns here and here we have the correlation. Now, we have not done that. On the data frame, we are trying to find out the heat map. So these are the indexes, 0th index, this index, this index, this index, and these are all the columns. So if we consider in each row, we have some columns and we are considering individual values. So there is no correlation at all because we are not considering one column with another column over here. What we are doing, each column and in that particular row, that value. So individual values we are targeting, right? This is suppose index 1, index 2, index 3. And we have column A, B, C. So we are taking suppose index 1 and column A, this value. Then we are taking index 1 and column B, this value. Index 1 and column C, this value. Similarly, we are taking index 2 and this column, index 2 and this column, index 2 and this column. Means individual values we are taking one by one. So definitely there is no point in finding correlation. And if there is no correlation, the correlation coefficient is 0, which indicates this particular color. And hence the whole heat map is of the same, this color indicating 0 correlation. Now, if we find out the correlation structure and find out the heat map on that, we are seeing that a Boolean data frame we have taken, in which all the values are same, all the values are false. In such a case, when we try to find the correlation, you can see that if everything is false, means all the values are false. That means everywhere we have the same value, means every column is equally, positively, perfectly correlated with each other. That is why the correlation R is equal to 1. That means we have this white color in our entire heat map. It is not that it is empty or output has not come. Output has come, but it is white in color and it is correlation is 1, means perfect positive correlation, because all the values in the entire data set is same. That is false. Now let us have the correlation on a proper structure. That means we are taking this particular thing, we are doing it, in which we'll get all the columns here and all the columns here, and correlation of fair amount with fair amount with pickup longitude, fair amount with latitude, fair amount with longitude, fair amount with and then pickup latitude with fair amount with this, we are finding out the correlation. Right? So you can apply the concept of correlation and see that if this is minus something, what is the correlation? If this is positive, what is the correlation? If it is closer to 1, it is positive correlation. If it is closer to -1, it is negative correlation. So we know that if the correlation coefficient is closer to 1, then it is strong positive correlation. If it is equal to 1, it is perfect positive correlation. If it is equal to -1, perfect negative correlation. If it is closer to -1, it is strong negative correlation. And if R is 0, there is no correlation. Okay, you can apply that on this data set. Now we get a proper heat map. So the syntax is using Seaborn library. We have written import Seaborn as SNS. So using SNS, we can access the functionality defined within Seaborn. Heat map, pass the correlation structure. Annotate equal to true means you want to annotate the correlation value on this particular cell. So along with color, you'll get the value also. If you don't write annotate, you'll only get the colors. But you want the exact value of correlation coefficient R, then you must write annotate equal to true. So you can see that along the diagonal, we have the value 1, which corresponds to white color, creamish white. That means each column is perfectly correlated with itself, isn't it? Now what we'll do is, we will divide the particular data set into features and columns for actually performing the machine learning algorithms on this. So our label or output is nothing but fair amount. And our features are other columns. Okay, so X should be a structure in which all the features are there. Now, since this fair amount, as you can see, is the first column. Okay, fair amount is the first column. So what we'll do, instead of writing all the feature names, we'll write X is equal to df of whatever df dot columns holds. We'll take from the first column up to the end. That means the zeroth index means zeroth column is what? Fair column that we wanted. We'll take from the first column onwards. That is the meaning of this. I hope you understood. And we know that the label is a single dimension structure, that is fair amount. Now, from sklearn.model selection, we'll import train test split, and then test size should be 70%. So training size is 20%. Or you can invert it also. Maybe you want more training, so you can use 70% for training also. And for testing, you can use 20%. And random state is 7. Okay. Then you plot X train, you print X train and X test, Y train and Y test. And you can find the total number of values also by saying length of something. Okay. Now, Y is divided into Y train and Y test. Training is 30% and testing is 70%. So 70% of Y is in the testing and 30% of Y is in the training. So total Y is 163040. 30% of 163040 is this much, and 70% of it is this much. So if you do 48912 plus 114128, if you add these two values, you should get 163040. Isn't it? Total number of Y train values plus total number of Y test values should be equal to the total number of Y values. Okay. Now linear regression will be applied. So import it, pass the X train, Y train for fitting for training. So you'll get the intercept as well as the coefficient, means intercept and slope. And now we have multiple features. This is multivariate linear regression. So you'll have a set of parameters. That means theta1, theta2, theta3, and so on up to theta n. And theta0 is nothing but Y intercept. These are the other parameters, and this is the intercept. Now maybe you want to print each of the parameters. So for all the coefficients in this coefficient array or coefficient list, for all the coefficients you are printing, theta0 is this much, theta1 is this much, and so on. Now you have trained the model. Now you want to test it. So do the prediction on the testing features and get the prediction. Now you can compare between actual and predicted label. We have always done this in linear regression. You can see that if the actual fair amount is 6.5, the predicted is 8.4. If it actual is 12, predicted is 10. If actual is 7.3, predicted is 7.1. So a small amount of error which needs to be minimized definitely. But we'll see how we need to manipulate either the random state or maybe the training and testing percentage and so on. Those are the hyperparameters. Now, as you can see, the index over here, we have done random shuffling, right? So the index is anything, like whatever index was for the particular row. Suppose these are our rows. If index was 1, 2, 3, 4, after shuffling, after taking them randomly, maybe they'll become 3, 4, 3, 2, 1. So we want to make this index again as 1, 2, 3, 4. Then what we'll do, we need to reset index. So on this particular data frame that we have created, which has the columns of actual value and predicted value, we will reset the index. So now what happens, whatever index was showing over here, that has become a separate index column. Do you observe? whatever index was over here, it has become an index column. And we have got new index serially, sequentially, 0 to n. But now we don't want this index column also. So what we'll do, we need to drop this column. So after resetting the index, drop the index column, and we need to find it along the axis. So now we have the perfect comparison data frame in which index is from 0 to n. And now if you want to plot a heat map between the actual value and predicted value, so you can see that along the diagonal, definitely you'll have perfect positive correlation. And along the other two spaces, that means between predicted label, actual label, what we have is 0.84. Now this is also close to 1, means we have nearly strong positive correlation. Okay, so this is what we have done in linear regression. Now we can apply random forest also. Before that, let us see certain metrics. Metrics evaluation can be R2 score. We know that R2 score must be equal to 1. That time we can say that actual value and predicted value, the difference between them is 0. So here R2 score is 0.6, okay? Almost 0.5. It is not perfect in prediction. We know that. Then mean squared error. Mean squared error, the formula is 1 upon 2m, summation of difference between actual and predicted squared. Okay? And similarly, we can also find out the root mean square error. Root mean square error is nothing but square root of a root mean square error. Root mean square error. Square root of mean square error is equal to root mean square error. Now, similarly, random forest regression we can apply. We have already seen an example. We have applied linear regression. Now, let's see random forest regression. So, we are taking n estimators, means number of trees you want to build before taking the prediction. Now, in random forest, we know it is a collection of trees. So, this is the data set. We'll have subsets. And we need 100 such decision trees to be made over these subsets. 100 splits, 100 subsets, 100 times decision tree algorithm will be applied individually on these subsets. And then we'll fit the model on training feature and training label, and then we'll predict based on X test, and then the predictions we will get. So based on the predictions, let us find out the accuracy also. R2 score, it is 0.8, quite close to 1, which is less difference between actual and predicted value. And then mean square error, we have found out the difference between test and prediction. Mean square error, we have found out, and root mean square error, we have found out. In NumPy library, if we call the square root function on the mean square error, we'll get the root mean square error. So this is it in the first practical. I hope this series was beneficial, in which first we understood some basic concepts like heat map, box plot, correlation, median, mode, and all such things. And then we've learned about linear regression, cost function, hypothesis, then what is mean squared error, gradient descent algorithm. Then in decision trees, we saw when the features and labels can be continuous or categorical. Then we saw ensampling technique, that is random forest. Finally, we applied all those concepts on the first machine learning practical, in which we predicted the fair amount from one location to another location for an Uber drive. So thank you for attending this series in which we have completed the first practical. I hope it was beneficial. Thank you.